Okay, welcome everyone. Very happy to have Chiara Caprini today. Chiara, I won't go into the full details of her career because we don't have time for that anyway. And even though Chiara began quite recently, she still has an impressive career done up to now. So she had a PhD in Oxford University already, and then moved to Geneva University, moved then back to some time in France at CEA, and then joined finally CNRS in 2008. So we were quite happy to have her around, and she was working at APC, unfortunately, I should say. Anyway, I didn't say that. And but really, unfortunately for CNRS at least, she went on leave. When was that? 2021?
Yes.
Yeah. To be back in Geneva, where she has a lot of connections, physics, from the physics point of view. And she works both at the University of Geneva and CERN. And she's actually, if I understood properly, trying to make the connections between those two centers for working in gravitational wave fields, sorry. And she's been involved in a lot of topics, beginning with cosmology and really almost everything you can think of in cosmology, from plasma physics in turbulences and creation of primordial magnetic fields and perturbation theory, and what else? Dark matter, dark energy. I think that's almost everything. Yeah. Everything in cosmology. And then, of course, and for the last some years, been focused on gravitational waves, produced either by bound binary systems, essentially gravitationally bound systems, or cosmology, early phase transitions, or inflation, or whatever is the stochastic background. So, in other words, she's really into that and seriously into that. And also, I should mention that she has had a lot of responsibilities. You were the head of the GDR Ondes Gravitationnelles at some stage. And she's also part of the astronomy working group in LISA. And she's also the founder of the cosmology working group, still at LISA, which you headed for a while. I don't know if you're still the head of that. You're no longer the head of that. But at some stage, when you're heading something, it's good to move on, as you know.
Younger people now leading that.
And so she's perfectly fit to, I mean, she's both a cosmologist working with gravitational waves and very much involved in LISA, and therefore presenting something on cosmology with LISA is really appropriate. So thank you very much and welcome here.
Thank you. Thank you very much for the invitation. It's a pleasure to be here today. Yeah, so I will present the case of cosmology with the LISA mission. And my slide, okay. So what is important to notice as the first message is that LISA has not been conceived as a cosmology mission, but as an astrophysics observatory. That was the main idea behind it. But actually, turns out that it can provide new information, a variety of scales, so really from galaxy to Hubble scales, and from the present time back to the very beginning of the universe. And so it is a sort of serendipity. It can be used as a cosmological observatory as well. And it can test both the late-time universe through the emission from compact binaries and measure cosmological parameters with that. We see how, but it can also test the very early universe thanks to gravitational wave signals from possible processes occurring in the very early universe. And this is going to happen because LISA is going to fly in 10 years from now, but as we will see, provided we are able to fully address the challenges which are presented by the LISA data analysis. Okay, so 2 words on the mission itself. So LISA aims to detect gravitational waves in space. the reason why one goes to space is because there is no seismic noise, and so one can access much lower frequencies, also because the observatory can have much longer arms. And what is planned is 2.5 million kilometer arms that leads to a frequency of detection between 10 to the minus 4 Hertz and 1 Hertz. So the Earth-based one, they are between 10 Hertz and 1000 Hertz. So you see there is a real change in the frequency band. That's why it is so complementary also from the point of view of sources, as we will see. So the configuration then is 3 satellites at this distance, 2.5 million kilometers, and they are orbiting on the same orbit of Earth, following Earth around the Sun. And it is a survey instrument, so there is no pointing. It's a continuous sky observation. And in each of these spacecraft, there will be two masses, which will be in free fall in one direction. And the reading will be done by lasers that are propagating through between the spacecraft. And the point is that, so as you know, the typical amplitude of a gravitational waves, which is then the strain, is 10 to the minus 21. So on 2.5 million kilometers gives a picometer displacement of the masses. So this is the sensitivity one needs to reach. And it has been demonstrated by the Pathfinder. There is a Pathfinder that is possible to put masses in free fall with such a precision that then it is possible to pick out these small disturbances. Of course, there are, if one is able to beat down the noise, but this is now clear. And so the schedule is that it has been adopted early last year, accompanied by a science red book from which most of the seminar is also taken. So if you want information on the mission, science is a good reference. In the next 10 years, it will be constructed. 2034-35 is launch. It then takes 1.5 years to get to orbit. And then basically the nominal mission duration is 4 years. But I will show results also for 10 years because everything on board is not tested, but ready to last for 10 years. After which the orbits will become unstable, and so the constellation will be gradually lost.
Sorry, why does it take 1.5 years to get to orbit?
Because it's far.
It's not further than L2?
It is, yes.
Okay.
Yes, absolutely. So, right, and then now the situation is that there is in place groups that are starting the NAT analysis preparation, and the LISA consortium is now rebooting. Okay, so this is the very general situation of gravitational waves. Here you see the frequency in log space and the span of the observatories that are there, from very low scales corresponding to the horizon or the size of the universe today, so this is the cosmic microwave background, to pulsar timing around the nanohertz. The LISA band is around the millihertz, and terrestrial interferometers is around 100 hertz. And each frequency band access different sources. So that's the key point. And for example, you see supernovae are typical of terrestrial interferometers, but compact binaries, such as stellar mass black hole binaries, they can be picked up by both, as we will see. On the other hand, as you get more massive, the emission transfers to lower frequencies. So LISA, the best sources for LISA are massive black hole binaries from 10 to the 4 to 10 to the 7 solar masses. And then we, as the object becomes more massive, one goes to the pulsar timing array band. And then, of course, in the early universe, this is all physics beyond the standard model, and so one can have any kind of frequency you wish. Okay, so this cartoon represents what we expect LISA to detect. Of course, it's a new window. Okay, so this is the best we can predict, but there might be surprises, we will see. So this is a function of the strain as a function of frequency. The green curve here is the instrument sensitivity. And then this colored line represent different sources. So the first thing here, you see, the sensitivity will be damaged somehow by the galaxy signal. These are unresolved sources in the galaxies, like white dwarf binaries. This is all the galaxy. Instead, these are the resolved sources from binaries in the galaxy, with some of which we know the existence because we observed them. These are binary pulsars. Then there is going to be these lines here are what we call EMRIs, so extreme mass ratioing spirals. This is a massive black hole at the center of the galaxy with a smaller compact object orbiting around it. These lines here are stellar mass black hole binaries. These are those that have been, now they are regularly detected by LVK. So LISA picks them up earlier in their evolution. And then there are here the massive black hole binaries, which, as you see, these are really the main sources with the highest SNR, really, for what the observatory has been constructed or projected. Right, so each of these sources will have a different waveform. So the signal will look very different. And what is the point, very different from Earth-based interferometers, is that actually in LISA, these signals they will all superimpose, and it is really signal-dominated instrument, not a noise-dominated one, and therefore, so this is the interferometer signal as a function of time. The real challenge is how to distinguish all these different kind of sources. These, for example, you see, these are massive black hole binaries. So these are the highest SNR, but the green thing is the background from the galaxy, which is modulated on a yearly basis because the interferometer changes orientation. And the red is the instrument noise. And so the analysis will be done in Fourier space. This is the same image now in Fourier space. With the black line, the noise power spectral density of the instrument. And so the point is that you see there is a large number of overlapping sources. There are confusion noises from unresolved sources, here typically the red one. It is not possible to cross-correlate signals. So LVK, they measure actually their signal because the noise in the two interferometers or three interferometers is uncorrelated. And so they put together the data and they look for a correlated signal and they say, okay, this is not noise. This is a signal. With LISA, it won't be possible because the three arms have a correlated noise. So this technique we cannot use. And there is also no equivalent of the L-links downs for pulsar timing arrays. You know, pulsar timing arrays, they look for this particular correlation pattern between the angle of the pulsars. And that's what tells them that actually, yes, we are measuring gravitational waves. There is no equivalent in LISA. So it is really, I mean, something that one needs really to resolve all this confusion to get to the data analysis. And the other fundamental point, especially for stochastic backgrounds, is the fact that the instrument will fly with a noise model, of course, but it is tested on ground. And once in space, there can be surprises on how the device works. It's the first mission of this kind, so we will see. Okay, and now the current plan is to construct what is called a global fit procedure, which is an iterative identification of each source type, starting from the loudest one, and at each iteration you have a better characterization of each of the source until you reach the end in which there is the instrument noise and also all the residuals from the imperfect subtraction of the other sources. Okay, so many groups are working on putting together this data analysis. And now what we are going to do is that we will proceed source type by source type and highlight the use of all this category of sources for cosmology. Some have no use, some have use. And what we will see is that there are sources that can be used to probe the late time expansion. There can be stochastic signal from the early universe, and there is sources that just produce foregrounds that are annoying and we would like not to be there. But of course, they carry a lot of astrophysics information. So, okay, so I will start with the compact binaries in the galaxies. So these are extremely numerous, and these are really quasi-monochromatic permanent gravitational wave signals because they are in the spiral phase very far from merger, and very many sources are expected, and they are around 1 solar mass, 10 to the 5 years from merger. If you put this in the Newtonian waveform, you get 3 millihertz, so that's there is a lot. Concerning cosmology, what they produce is this confusion noise that then hides possible stochastic backgrounds. This is in general needs to be modeled starting from a galaxy model, so how these sources are distributed and how many they are and what kind they are in the galaxy. And then you iteratively subtract those that are loud, putting a signal to noise ratio criterion, and then in the end you are left, so this is the original galaxy, and then you subtract all those that you can see, and you are left with some foreground. After many iterations, at some point you are not able to get any other result source here, and so you have your foreground prediction. And how you can distinguish from a stochastic background from the early universe. Of course, this provides you a signal template. So you know the signal spectral shape and you can use it to distinguish it from other things. And one can also exploit the fact that this is modulated in time on a period of 1 year, and while a stochastic background is stationary in the frame of the Hubble flow, of course, not in our frame. But okay, so not much to say about galactic binaries for cosmology, but now we go to massive black hole binaries, and there is something to say. So this is my image of Marta. So these are the black holes that are observed or indirectly observed, we can say, at the center of many galaxies. And because the galaxies collide, hopefully they do exist in binaries. Now this hopefully, I think, is no longer the case to say it, because if pulsar timing arrays have really seen the stochastic background from supermassive black hole binaries, then we know that they are in binaries. So LISA then can detect, as I said, from 10 to the 4 to 10 to the 7, more or less, binaries, black hole binaries, and it detects the spiral, merge, and ring down. So the entire phase, pretty much like LVK do for stellar mass ones. And the signal duration can be from few hours to several months prior to merger, depending on the state of the binary. And also what is very important is that LISA can pick them up to redshift of 20. So it's really, you have the full access to the population, so you can then probe the formation and growth and possibly distinguish formation scenarios for them. Right, and this was just to say that indeed now we do have indication, right, both in the gravitational wave band and in the electromagnetic band that these very massive black hole exist up to high redshift. So this is very good news, I think, for LISA. And now let's come to cosmology. So how are these sources useful for cosmology? Well, apart from the fact that in principle you can study the formation of structure, but it's a bit difficult to access, but indeed they can be used to test the background expansion of the universe, because they are expected to be accompanied by electromagnetic counterparts. Okay, and this happens if they occur, this merger, they are surrounded by a gaseous disk at the center of the galaxy. And then what happens that you pick up the two polarization of the gravitational wave, and with that you have a direct measurement of the luminosity distance of the binary. Unfortunately, you have no measurement of the redshift. Okay, so you cannot construct the Hubble diagram, which is luminosity distance versus redshift, directly from the gravitational wave emission. But if you have an electromagnetic counterpart, this gives you the redshift, and then you can use it to study the background expansion of the universe. And so it's a bit the converse of supernovae, right? The supernovae is difficult to get the luminosity distance. You have to cross calibrate, but you get the redshift very well. And here it is the converse situation.
Can you just explain qualitatively how that works, those two equations, because I've never seen them before?
So this is the emission, okay, and it depends on various parameters. Some parameters are also hidden here. This is really the waveform. And basically from what you have here, and also by measuring the variation of the frequency, you get the mass. Okay, and then with the measurement of the two polarization, you access the luminosity distance. Okay, so basically what is needed, so we did this analysis together with Marta. The first thing one needs is to select events with a good sky localization, of course, to be able to pick up the counterpart. There are two problems here. The first thing is that the nature of the counterpart is yet unclear, because we haven't observed any of these mergers, and also there is a weak lensing that is going to affect the measurement of the luminosity distance, actually inducing errors that are in many cases bigger than the measurement error of LISA. So we have built an approach in which we start from simulated catalogs of these binaries. We perform parameter estimation by LISA. We get an error on the sky localization and on the luminosity distance. So the one of the luminosity distance, we add the weak lensing and then we put it aside. And the one of the sky localization, we use it to construct some strategy for the detection of the electromagnetic counterpart, which consists in general either, but this works not very well to detect directly the host galaxy, or you first localize the source better than what LISA can do with some radio counterpart or with some X-ray counterpart, and then you point an optical telescope to actually get the redshift, and then you construct the Hubble diagram. And this is what happens just with LISA. You see, these are all the parameters that go in that waveform that I showed. And this is the distance. I highlighted the distance and the two parameters that gives you the sky localization. So it works for sources that have a high signal to noise ratio. It works well, the parameter estimation. And now these are the distributions of the events starting from the catalogs. So these lines, so these three are three different massive black hole binary formation scenarios. This is what the catalog tells. This is what happens when you impose that LISA can localize them. No, sorry, that has a SNR larger than 10. This extra cut in the numbers is because you can localize them. And then we have two scenarios for the detection of the counterpart. One is pessimistic and the other one is optimistic. And this will provide counts so in the end, we have a prediction of average number of massive black hole binary mergers detected by LISA and for which we know the redshift. And the important thing for astronomers here is that the redshift goes, cluster from 2 to 5. So one can go at high redshift. And this is the key point also for the cosmology. So you can test the expansion of the universe, not between 0 and 2, as you can do with supernovae, but, between 2 and 5. So that's new. And here I will show some forecast constraints. And the important thing that, unfortunately, one needs to point out is that the errors on the cosmological parameters are dominated by statistical fluctuations in the realization. Okay, so it is our astrophysical uncertainty that will provide, so we have simulated 90 catalogs, and of course the sources fluctuates and the number of sources fluctuates and the errors fluctuates with that. So these plots have the fraction of the realization as a function of the 90% error on the particular parameter. Here is the Hubble parameter today and omega matter. So the error on little h are about 5% in 4 years and can go down to 2% in 10 years. So you see, this is not really competitive with what Euclid will do, of course, or CMB already does, but it is a new channel. That's the thing. For this particular model, which is the usual H0 omega M1. But we have realized that at higher redshift, it gets better. So here you see, this is the 90% statistical error on H as a function of redshift. And so this is the error at redshift 0, but you can go better at a higher redshift. This is the fluctuation from the realization, and the colors are the three population scenarios. So we have pushed this analysis with other redshift models. One possibility is to say, okay, at redshift between 2 and 5, the universe is matter dominated. And if it is matter dominated, that's my parameter, right? The Hubble factor at a pivot redshift and the distance at a pivot redshift. And this is how LISA can perform at different pivot redshift, measuring the Hubble factor or the co-moving distance. So you see, for example, a measurement at redshift 5 of the Hubble factor to 10% is something that is pretty interesting. And this is an analysis in which we just model the luminosity distance as a function of redshift with a spline. So we put no physical model, whatever, there, and this is how LISA can measure the different nodes of the spline in redshift, both for the luminosity distance and H. So this was all done using massive black hole binaries. So they are useful sources for cosmology. Now I'll go quickly through extreme mass ratio in spirals. So these are binaries for which the masses of the two objects are very different. This is the mass ratio between 10 to the minus 7 and 10 to the minus 4. So it is one central black hole at the center of the galaxy and a compact object merging into it. Okay, so we know that these things exist. We have observed them in our galaxy, right? Not the merger. We observed larger, much larger orbits, but we know they are there. And a lot of science can be done by LISA with those. The point is that the rates are highly uncertain, so we will know them only when we turn on the the instrument, but they in principle offer the opportunity to map the full black hole population in the universe and study the environment of the galaxy centers. But so for cosmology, unfortunately, they have one bad point and one good point. So the bad point is that they do produce a foreground that very much depends. So this is again strain as a function of frequency. You see the different models. So the fact that the rates are highly uncertain, the predicted foreground can vary by 3 orders of magnitude. So if it is down there, we don't care. But if it is there, it's extremely loud foreground for cosmology. They can also be used as dark sirens. Dark sirens are sources for which there is no electromagnetic counterpart. So this indeed for these EMRIs, there could be tidal disruption events, but I think they are not, they are too faint at the redshift at which LISA can measure these things. So there is no electromagnetic counterpart expected. But you can, so then the question is, okay, you observe the gravitational waves, you get the luminosity distance, but there is no electromagnetic counterpart. How do you get the redshift? And this particular method of dark sirens proposes to get it statistically. So you cross-correlate your measurement in gravitational waves with a galaxy catalog. And you perform a statistical analysis that in the end allows you to reduce the error box in redshift and localization around your gravitational wave source, and you have a measurement or an idea of what is the redshift of the source. Of course, to be effective in this statistical method, you need very many sources. And here, so this paper did the prediction on the cosmological parameters of these particular sources using obviously one or maybe 3 of these models, pessimistic, middle, and optimistic. And this is the result for the fiducial model. And you can have a 3% constraint on the H-naught. And now these sources, instead of the massive black hole binaries that are distributed between 2 and 5, they are distributed at earlier redshift. So you can hope to measure the dark energy as well. So with the massive black hole binaries, you know, dark energy has no effect after redshift 2. But these sources are more similar in the redshift distribution to supernovae, and so you can hope to get W naught. WA, no. But then what is important is that the full potential of LISA is actually not yet assessed because, in principle, LISA accesses both kind of sources. And you see, you have one population that goes between, let's say, 0 and 1, 2, right? And the other population that goes from 2 to 5 in redshift. So if you are able to combine the two analyses, you can constrain the Hubble diagram much better. Okay, so unfortunately, it's not easy to statistically combine these two measurements in a correct way. So Laghi et al., they are working on this since now a few years. And hopefully then we'll get a sub% level of H-naught and a few percent on omega n. That's what we hope. Okay, how am I doing with time? 20 minutes, guys, I need to speed up. So, okay, now we look at black hole binaries of tens of solar masses. So these are the sources that are observed now by LIGO Virgo Car. Okay, and LISA picks them up earlier in the inspiral phase. So you see, you get a shear mass of 25 solar masses, 10 years from merger, and you fall in the milliards range. These are quasi-monochromatic sources because they are 10 years from merger, so much before their merger, but some of them, you see, here you see the strain as a function of frequency for different time to coalescence, so larger than 10 years, from 5 to 10 years, smaller than 2.5 years. And typically these kind of sources you can detect them. You can perform parameter estimation from among the parameters. There is the time to coalescence, and therefore you can then say to Earth-based interferometers, look, we have seen a binary that is going to merge 8 years from now with a precision of 1 hour in your band. Okay, so there is this opportunity of performing multi-band detection, which opens up a lot of science cases. So again, focusing on cosmology, unfortunately, the science that can be done with them strongly depends on the number of detectable sources. And this is why they can't be used for dark sirens, because they are not numerous enough. And they also produce, as well, a stochastic foreground, which we have actually evaluated in this paper. And basically, you apply this iterative subtraction method, which is what I described also for the galaxy. So you construct a population, and we have used LIGO Virgo Kagra population models to simulate the population. And then you simulate the instrument, and you subtract the sources that you can individually detect. And at some point, there are no more sources, and you are left with the foreground. So with this method, you get both the number of sources and the foreground. Of course, those that are the resolved one are those that are closer to merger because they gain in signal-to-noise ratio, and they are closer to us because as well the signal is stronger, while the foreground is done by the distant and inspiraling sources. And therefore, what is important is that the prediction of the foreground depends on the population at high redshift, which indeed LIGO Virgo Kagra do not constrain. So that is our prediction, very boring power law. It actually follows the analytical prediction, but what is important here is the source, the amplitude of this foreground, and this is the amplitude at a fixed frequency. And what you observe here is our prediction on the amplitude based on the uncertainty of the population from LIGO Virgo Kagra. Okay, so the amplitude, of course, depends on the detail of the population, and this is the constraining power of LISA from this detection. Okay, at different percentile. And so the bottom line is that the error with which you actually can measure this, the amplitude of this background, of course, it increases as the amplitude decreases, but it is always smaller than the uncertainty on the population from LVK. So you can, in principle, access some information on the population by this foreground detection. Here is the converse result. So here is the result that we get on the number of sources, okay, number of events, depending, so these three curves depend on the signal-to-noise ratio threshold that we put to call a source resolved, 8, 6, and 4. If we put a low signal-to-noise threshold of 4, we have very many sources, but the most clear, probable one is 8, and for 8, you have a median of 5 sources in 4 years. So these are really, rare events with 2% probability of no sources and 10% probability of more than 10 sources. So, however, the multi-band ones, okay, they are a third of the total, so we do get a few. Our prediction is a few multi-band events in 4 years, and of course, if then you have a mission for 10 years, this number increases. And here is the last thing I wanted to say about this before the bad news, and is the fact that you see, so the number of resolved sources are too small and dominated by statistical fluctuations to be exploited to constrain the population. This is what LVK does. They see their sources and then they infer the population characteristic. With 5 sources, you don't do it, of course. But LISA also see the foreground, which LVK for now hasn't seen. And the two measurements have opposite correlations. So here are the parameters on the population, like the merger rate, the slope of the merger rate, the shift, etc. And this is the amplitude of the foreground, and they correlate in opposite direction, you see. So it means that you have both, if you have both measurements, then you can extract some information on the population characteristics. So LISA can be useful for this. For example, if you have a lot of individual sources and a very high foreground, it tells you that your population is wrong. However, unfortunately, maybe this foreground, that is the green line here, it might be completely obscured by another kind of source, which are extragalactic white dwarf binaries that, according to these works here, will produce a much higher noise, or call it foreground, in the LISA band. So let's see. I think this is nowadays quite standard that populations of white dwarf do give a foreground of this level. So it might be that this science with stellar mass black hole binaries won't be possible, unfortunately, if we cannot access the foreground. Okay, and now in the last, I suppose, 10 minutes or whatever it is, I focus on the cosmology of the early universe. Okay, and these are the possibility to have stochastic gravitational wave backgrounds from the early universe. So the point is that the gravitational wave emission processes in the early universe, they form a fossil radiation. This is very much like the cosmic microwave background. And if you're able to detect it, you have direct information on what is going on in very early stages of the universe evolution that you cannot access with photons, because photons are strongly coupled earlier than when the universe was 370,000 years old, okay, which is the CMB formation. Of course, we can access much earlier epoch through CMB anisotropies. We can access inflation and the production of the fluctuations that gave rise to all the large-scale structure today. So with CMB, we do access the very early universe, but between inflation and the recombination, there are a huge amount of a long epoch, right? Because inflation is at energy scale at 10 to the 16 GeV. Recombination is at 1 eV, 3 electron volt, okay? And so all this part here is dark. We cannot, photons are tightly coupled, we cannot probe it. Gravitational waves can probe it because they propagate freely. They have no problem of tight coupling because they interact so little, of course. So that's two aspects. They come because they don't interact, so then we cannot access them because they don't interact. So it's a bit like this. Anyway, but they do have an amazing discovery potential, obviously linked to high energy physics, because you know that the earlier we go in the universe, the higher energy scales we actually are able to access. So stochastic backgrounds offer the opportunity to test beyond standard model physics, complementary to particle colliders, and they can clarify open problems such as the nature of dark matter, because they can test gravitational wave signal in scenarios that provide dark matter candidates. They can test the gravitational wave signal coming from scenarios which provide the matter-antimatter asymmetry. They can test the occurrence of grand unification. So they can test the nature and the characteristic of inflation. So it's really a lot of science that can be done. Okay. Of course, the problem is that all this freedom in modeling these particular sources turns into a bad point, it is impossible to make a definite prediction on the signal amplitude spectral shape, which is exactly what you would need to access it easy with your detector. So the outstanding challenge here is how to distinguish the stochastic background signals from the early universe, from the instrument noise, and from the astrophysical foregrounds. Okay, so it is not at all granted that the science will be there. First, because we don't know if the signals are there, and second, because even if they are there with the right amplitude for LISA to detect them, we are not sure we will be able to assess their presence. Okay, so this I already said a bit, but example of possible sources in the LISA band, there has been a series of papers from the LISA Cosmology Working Group recently that have reassessed the observatory potential to access all these science cases, basically during inflation. The most interesting one are the first two. You can have tensor fluctuation produced at second order from the scalar ones. This is a guaranteed signal. For LISA to pick it up, you need an enhancement of the scalar fluctuations. Of course, if they are 10 to the minus 5, you don't get the second order tensors. But it is an interesting, very interesting science case because it also produces primordial black holes. And thanks to this particular mechanism, LISA can test the window in primordial black hole mass, which is the last one in which they can be the totality of the dark matter. Okay, so there are no other constraints in that particular mass window, so it's extremely interesting for LISA. And then you can test also the presence of other kind of fields during inflation other than the inflaton. But also the other science case is that it can test the presence of gravitational waves from other kind of phase transitions instead of inflation that can produce a strong signal, either from topological defects, if they leftover topological defect, or from, if they are first order, from the dynamics connected to the wall. We will see that. Is the next slide. Now, the point I want to make here is that there is a great variety of spectral shapes depending on the source. So here you have the energy density in the stochastic background fractional, so with respect to the critical energy density today as a function of frequency. You see the observatory sensitivity, and these are motivated science cases. Okay, so this is the signal for cosmic strings, so topological defects, if they are the signal that PTA measures. Okay, so you see how LISA can get it. This is the signal if the totality of dark matter is in primordial black holes of sublunar mass. And this is phase transitions that provides a dark matter candidate and also baryogenesis. And these are the forecasts. Okay, so it is difficult I mean, there is a lot of science, well-motivated science, but it's difficult to disentangle, right? So the first question is, provided we know the signal and noise spectral shapes, and provided we do detection, can we infer the source parameters? First question. Suppose that we can infer the spectral shape and we can reconstruct then the signal origin. No, sorry. Suppose we know the noise spectral shape. Can we reconstruct the signal spectral shape to understand its origin? And what can we do if we actually don't know the noise spectral shape? Okay, so it is a delicate situation. So here, among all the signal, I want to point out what I believe is the science case for LISA here, and it is signals from the electric phase transition. Why? Because the sensitivity, frequency sensitivity range of LISA, which is the millihertz, coincides with the TeV energy scale in the early universe. So really, there's another serendipity. LISA provides access to possible gravitational wave signal at the scale of 100 GeV, 1 TeV, up to 10 TeV, which is the frontier between tested physics and new physics. So it's really important for us. The electric phase transition in the standard model is a crossover, right? But we know that the standard model is wrong, so we need to go beyond the standard model. And in some scenarios that were proposed before gravitational, we knew that gravitational waves were interesting, the electric phase transition is first order and therefore can produce a gravitational wave signal together with possibly baryon asymmetry and dark matter. First order means that in the potential of the scalar field that undergoes the transition, you get a barrier. And so you can actually, so the field will thermally overcome or quantum tunnel across the barrier. This forms bubbles of the true vacuum in real space. So this is field space, this is real space. These bubbles then expand, collide, and at the collision, you know, the spherical symmetry is lost, and therefore you produce gravitational waves. These are processes involving, if the phase transition is strongly first order, involving a lot of energy, and therefore they can be powerful sources of gravitational waves. And also these collisions, they perturb the universe fluid, leading to possibly turbulence, sound waves, etc. And so these are examples of signals with respect to the LISA sensitivity. And so we actually did a more accurate analysis, and you see this is one example of signal. This is a template-based reconstruction of the thermodynamic parameters of the phase transition. Template-based meaning that we assume we know what is the signal spectral shape, and it is governed by all these parameters, and LISA can pick them up. Of course, here what we do is that we are assuming that we do know the noise, so the noise shape. So the noise is parameterized by two parameters that are also reconstructed, is this A and P. Okay, but so there is some freedom in the noise, but not on the noise shape. So that's, you know, not exactly what is going to happen in reality. But if we are able to do these kind of things, so these are the reconstruction of the thermodynamical parameters of the phase transition. From the thermodynamical parameters, you can map the parameter of the particle physics model. And here you see, this is a Z2 singlet extension of the standard model, and you have the coupling and the singlet mass. And this is what LISA can do, okay, depending on the singlet quartic coupling. And this is what FCC and high luminosity LHC can do. So it is actually interesting that you can have a coincident signature. And this is another model, you know, in which you have a first order electric phase transition. And these are the parameters as well that LISA can test. Okay. And now I just want to close with, again, digging a bit more. So I showed you the scientific potential if we know the noise. Let's dig a bit more in what happens if we don't know the noise. So is it possible to reconstruct the signal spectral shape, which is fundamental to identify the gravitational background sourcing process, provided we know the spectral shape? And this, you see, is something that is a relevant question, because in the analysis I showed you before, we were assuming the signal spectral shape. We are not reconstructing it. So now here we take the same model. And there is this nice analysis in which, assuming just that we know the noise spectral shape with some uncertainty, and we know the galactic background foreground, so the galactic foreground spectral shape, we know the stellar mass black hole binary foreground spectral shape, we can reconstruct a primordial signal by looking at each frequency, how much excess there is with respect to what we know. And you see that you can actually, if your uncertainty is pretty small on the noise, you can actually see that there is something more there. the other analysis is pretty similar, but it does assume this two-parameter model for the noise. And here, so here you divide the frequency in bins, and you look for a power law in each bin. And here the point is to see, can you actually reconstruct the spectral shape bin by bin? And if the signal is strong enough, it is possible. So these are the kind of analysis that we will do, assuming that we know some noise. If we don't know the noise, then we can hope to reconstruct it starting from a known signal. Okay, so here, in this analysis, the noise is parameterized as a series of, as a spline, so completely free. And there is in the data, in the simulated data, the galaxy and the stellar mass black hole binary foreground. And the analysis reconstruct with known spectral shape, and the analysis reconstruct these two together with the noise. So that's where we are for now in this problem of distinguishing the noise from the signal. Okay, so I'm done. So conclusion is that I hope that I convinced you that for not having been designed to do cosmology, LISA performs pretty well. Concerning the constraints that LISA can put on the late universe expansion, they are not directly competitive with standard cosmological surveys, supernovae, BAO, CMB, etc., at least for the nominal mission duration of 4 years. But the measurement of the luminosity distance is direct and independent on the electromagnetic emission, in the sense that you don't need to cross-correlate with Cepheids of whatever. So these are measurements which are affected by different systematics with respect to the usual cosmological observables. And then what is the main point is that LISA has the potential to constrain the universe at high redshift. So assuming matter only, a redshift 5, 10% error on the Hubble parameter at redshift 5, and 2% on the luminosity distance. And with the spline interpolation, a redshift smaller than 3, 10% error on the Hubble parameter at each redshift node. Okay, so it does have its own way, its own thing to bring to the testing of the background expansion. And concerning the early universe, okay, so signals might seem speculative, but their potential to probe fundamental physics is great. And indeed, amazing discoveries can be around the corner. So, of course, LIGO, Virgo, Kagra didn't see background, okay, but they are less sensitive. And we have seen that different energy scales in the universe lead to signals in different frequency bands. So it's not because they haven't seen anything that there isn't anything in other frequency bands. So, and the point here is really to probe physics beyond the standard model. And I have told you about the 3 very motivated science scales for LISA: the electroweak scale, complementary to particle colliders; second order perturbation, when primordial black holes can be the totality of the dark matter; and cosmic strings in coincidence with PTA, but actually even lower signal. Okay, and of course, I try to convey the message that the detection is very challenging, because you must control both the prediction and the detection of the spectral shapes, because if you don't know the spectral shape, you cannot know where the signal comes from, right? And then you have to be able to deal with the foreground from astrophysical sources. And the problem is that a decent knowledge of the instrument noise is not clear that we will have it with LISA. Thank you very much.
Okay, so I guess there are many questions. If you don't mind, since I have the possibility, I will ask the first question. Okay. You mentioned that the cosmic strings are in coincidence with PTA. Can you say what is the value of G mu, which it corresponds to, and how far below can you go?
Yeah, I think it's about 10 to the minus 11. So 8 times 10 to the minus 11, that's what would fit the PTA data. I know that there is some tension with the slope, okay? So it's not, of all the early universe signals, cosmic scenes is not the one that fits the best PTA data, right? With LISA alone, one can go down to G mu 10 to the minus 16, 17, depending on the model. So it is promising, yes.
Right. Yeah.
I have a question on the primordial black hole scenario. What you call the stochastic gravitational wave background in that case is the one produced at creation of those primordial black holes?
It is linked to the creation. So the idea is you have the usual scalar fluctuations from inflation, and then you put some exotic way to enhance them outside CMB scale. So where CMB has probed them, you leave them as they are, and then you put some kind of growth. It could be a bump, it could be a power law growth, etc. Now, at that point, because the amplitude of the scalar mode becomes order 1, at second order, it is again of order 1. It's not like, when it is 10 to the minus 5, at second order is 10 to the minus 10, the tensor you produce are very small. But then the scalar is of order 1 and can produce then a tensor, modes, so gravitational waves at second order, which are strong. And then at the same time, because the scalar fluctuation is of order 1, they can collapse as soon as they re-enter the horizon during the radiation dominated year. They collapse and form primordial black holes. So you do have a tensor signal which is generated at inflation. And then as the universe evolves, you form primordial black holes by the collapse as the scalar fluctuation re-enter the horizon. And you can actually connect the primordial black hole mass. So the primordial black hole mass depends on when they collapse. And when they collapse depends on when you have this bump in the scalar fluctuation. And in LISA, by chance, so you can access the tensor fluctuation from second order scalars in the frequency range that would lead to primordial black holes of sublunar mass or asteroid mass, which is the only region in which they can still be the totality of the dark matter. All the other masses are constrained, right? So it is nice to have this double testing.
Just on the, can I add?
Okay.
You, on this process that you described, you called it a quantum process in one of your slides, the second order perturbation. I don't see why it should be quantum.
This is not the second order perturbation. The quantum process is the tunneling. The tunneling here across the barrier can be quantum or thermal. No, there is a, so of course, what generates the scalar perturbation during inflation is quantum fluctuations, right? But then
the quantum second order perturbation generated by the coupling between the scalar.
Because they are quantum fluctuations of the metric, right? Just for that.
Classical process.
But then the formation of the black holes is, of course, is a classical process. Yes, absolutely. And also the second order sourcing is a classical process.
You mentioned that for measuring the redshift of the source variable diagram, you can cross-correlate with the galaxy catalogs,
yes.
But then you're limited by the angular resolution of the LISA detectors. So how well you can localize sources on the sky?
So that depends on the source signal-to-noise ratio. So in the particular analysis, I was not part of that analysis, but basically what they do, then they consider EMRIs. Depending on the source signal-to-noise ratio, you have a given sky localization. They select sources with SNR larger than 100, which means that you see them very well and you localize them pretty well. And then what they do is that they assume a cosmology. Okay, so they can turn this angular thing in some box, and then they do the usual.
So concerning your analysis of cosmological parameters like the Hubble constant, So LISA will detect merging supermassive black holes or quasi-supermassive black holes. And so there's a degeneracy, if you wish, between the astrophysics and the cosmology, right? So the astrophysics, you mentioned it from the simulations you've done from the models of Enrico Barros.
Yeah,
I
didn't do that.
Exploit. So my question to you is, if you consider the uncertainty in the astrophysics as a systematic, how important are the systematics in your error budget on the cosmological parameters?
The entire
And is the general feeling that we'll learn more about galaxy evolution or we'll learn more about cosmology?
Sounds kind of familiar, that.
So, okay, any of these plots shows it, right? So here maybe this is the number of sources, and here there are really the three models for the massive black hole binary production. So you see already how the number of sources varies. This model, of course, is the one that predicts the most of sources. The ability to do cosmology depends on how many sources are there. So it directly depends on that. And here, for example, the colored lines, so dashed or solid is a mission of 4 years or a mission of 10 years. So this is LISA, but the colored lines are indeed the astrophysical population model, and this is the fraction of realization because we have simulated 90 catalogs. Okay, so even within one single generation, massive black hole binary generation scenario, you fluctuate the number of sources depending on your statistical realization. So even, assuming the astrophysics, you still fluctuate. And so you see how the error can actually vary. If you take that you want something, at least 75% of the realizations to get your error, it can go, depending on the astrophysics, right, from something that is below 10% to something that is maybe 15%. It does change and vary a lot. It's forecast.
So you must be happy then with the new James Webb results full of these high redshift galaxies.
Yeah, Marta is happy. I am. But of course, it's extremely good news for LISA. And I don't know if you actually probably this model is more or less gone.
Just if I make another comment, 2035, okay, it sounds a long way away, but probably it's just tomorrow. But in 2035, there will be a bunch of other satellites observations. Are any of those complementary observations help you understanding what the background is for the cosmological signal?
You mean what the astrophysical foregrounds? Yes, indeed. So, okay. So, for example, LIGO Virgo Kagra will have gone at least through will reach their nominal sensitivity, and this, the expectancy is that the population constraint will be much better, and for example, this particular uncertainty here will shrink. So this for sure will help pin down the foreground. Now the problem really here is this one, because these are white dwarf binaries outside the galaxy, and there is no other probe that gets them. So here is my understanding, I'm not a specialist, is that really we will understand this the moment we turn on LISA.
Any questions? No. Sorry.
Yeah, it's on this. So you mentioned at the beginning that the galactic binaries, the signal is modulated over 1 year, so this helps you with subtracting them.
Exactly.
But for the extragalactic background, in principle, it should not be modulated. So
that's why it is a real problem. And you see here, it is plotted exactly like this. F to the 2/3, because there are very many, and to date, just as the cosmological one.
Question? Oh,
no, I can ask later.
Okay. Thank you again then.